Hey guys, this is going to be the exam 2 review, so I'm going to work the practice exam. Apologies in advance if you hear me breathing, the microphone is kind of finicky. All right, so I'm going to fly through this as I did on the last one, and if you have questions on it, either discuss it with your friends, bring it to me, bring it to Paul, depending on who your professor is, and we'll get it answered. And just like before, this practice test will be a really good way to study because the real exam will more or less be 20 questions from this. But we're going to be editing it a little bit more, so the questions won't be 100% similar, but it'll still be very much the same as the last exam. Okay, first question. What about the voltage drop given the capacitance, or at least we'll be able to find the capacitance, and the charge on two things? So relationship between charge and capacitance is this. Okay, and we're given C. Remember, C is purely a property of the shape of the objects involved. It doesn't depend on anything else. So here we have a formula for C for this specific shape, which is just told to us out of thin air. Okay, and I know every number in this equation except for one. Q is that on each plate, so I have 4e minus 9 equals 4 pi epsilon 0. A and B are 0.04 and 0.06. Okay, I'm going to simplify that garbage on the right. I've actually forgotten the value of epsilon naught, which is kind of funny. Minus 12. Okay. Being careful to group things in parentheses in denominators. Okay, and I'm just going to divide the left side by the number on the right side. I get V equals 300 volts. Big circuit question. The charge on the plate, so we're going to do our process of breaking down the circuit and then rebuilding it. So first we combine the two series capacitors into an equivalent capacitor. When you combine two capacitors in series, you have to do 1 over 4 plus 1 over 4, and then 1 over the result. So that gives you a capacitance of 2 microfarads here. And we combine two in parallel, you just add for capacitors, so we get 4 microfarads, 9 volts. Okay, now we've gotten it down to, oh, actually I realized I didn't tell you what is capacitor 3. So we're going to call this capacitor 1, this is capacitor 2, and this is capacitor 3. Okay, we're going to do QCV on every capacitor. And we actually might not need to go back this far, but this is just a reminder. Generally, you just want to solve the whole circuit. Okay, so once we've reached here, the whole point is that we know the voltage drop now is equal to the battery voltage, so 9. Q equals C times V, so 36 microcoulombs. Okay, now we're going to restore this equivalent capacitor back into two capacitors that make it up. Now, we combine two things in parallel to get here, which means they each share the same voltage as the equivalent capacitor. So each of them has 9 volts. Now, anytime I have two of Q, C, and V, I can instantly get the third by taking C times V to get Q. So I get 18 microcoulombs on this guy and 18 microcoulombs on this guy. Okay, now we technically already have the answer here. We have this 18 microcoulombs, so that is the answer. But I'm going to finish the circuit just so you know. We're going to transfer this equivalent capacitor back into the two real capacitors that make it up. And you combined two capacitors in series to get this equivalent capacitor, so they each share the charge on the plates. And now we are able to get V by doing Q divided by C. So it's 18/4 volts for each of them. And obviously this information is the same as we had before. We're just copying it back over. So this is a complete circuit solve, so it doesn't really matter what capacitor you're asked about or if you're asked about voltage. Okay, we're going out of order in this practice test. So this is guessing the current direction that gives a correct magnetic field. So these are just guess and check problems. Whenever you're given a B and asked what direction current would create this B, you're going to have to guess and check the current direction. So I'm going to start by randomly guessing into the page. Okay, so I'm going to assume the current goes into the page, and I'm going to see what happens at a point out here. Does the B field created by this current go in the correct direction, like this counterclockwise, or does it go in the opposite direction? Okay, so if I guess that the current goes into the page, oops, okay, the direction of the B field created by current, it's similar to IDL cross R. And remember, R is essentially the arrow pointing from the element creating the current to the observation point. So R goes like that, and I is into the page. And if we compute, and by the way, I and IDL are basically the same thing. It's the direction of charge flow. So if I do the right-hand rule on into page cross R hat, I get my thumb points to the right. So that would produce a magnetic field in the wrong direction, which tells me my guess that I was into the page was actually incorrect. So the answer is actually I is out of the page. Again, we guessed into the page, we got it wrong, which tells us I is out of the page. And if you do a right-hand rule on out of the page cross R, you'll get B points to the left at that specific dot. Worth noting, if you want to check the value of B at a different place, like here, R hat will change direction and the output of your thumb will change direction, but the answer will be the same. Right, because if you're checking at the bottom, you hope to God that if you got the answer right, your arrow points to the right instead of to the left like it did, like we had wanted when we were checking out this point. Okay, so either way will work. Okay, when you insert a dielectric, it weakens the electric field and voltage. That's sort of like the definition of a dielectric. It sort of blocks the electric field. It reduces how much electric field and voltage each charge creates. And it increases the capacitance. Couple ways you can see that. If you are really, haggard about it, you can do capacitance is charge over voltage, and voltage goes down, so C gets bigger. But honestly, I would recommend just using the equation C with a dielectric is the original C times kappa, where kappa is a constant greater than 1, the dielectric constant, like Teflon is like 2 or 3. So this tells you that C new is bigger than C old. Okay, another capacitance question, except this time it talks about the energy to charge a capacitor. So let's scroll down to our relevant equations about capacitor charging. Okay, let's see. We know the voltage and sort of the energy involved, and we're wondering about the capacitance. So I'm going to look for a formula that has like potential energy or work, voltage, and capacitance, which is actually the first one on the equation sheet. Work to charge is 1/2 CV squared. Okay, now we're being told things about the area of the plates. So for a parallel plate capacitor, C is the area of the plate times E naught over the separation between the plates. So I'm just going to make that replacement into our equation. And if we look at this, we actually know everything but 1 already. Or sorry, we know every number but 1. So work is given to us to be 40 joules. The area of each plate is given to us to be 0.04 meters squared, or sorry, 4 centimeters squared, which actually 4 centimeters squared. Ooh, this is tricky. I might actually remove this from, I might change the problem a little bit. I might have it say point whatever meters squared, but 4 centimeters squared, remember, 4 centimeters squared, you need to multiply it by 100 centimeters in 1 meter. You need to do that twice. So this is actually 4e minus 4, right? 4 divided by 100 squared is actually 4e minus 4 meters squared. Very, very, very tricky here. Okay. I will probably mark down that this is a trick question. Watch your unit conversions on centimeter squared. Okay, so now I'm going to move d to the other side and the 40 to the other side. Oops, sorry. Move d to the left and 40 to the right. So it combines with the 2 to give you an 80. Okay, now I'm just punching in my calculator, being careful to group things in parentheses. So I get, I picked a bad number. This is smaller than an atomic nucleus, which I made a mistake in the first problem, but apparently I tried to fix it in the wrong direction, so it's even worse. Yay. All right, 2 capacitors in series. You have to do the 1 over plus 1 over, so you have 1 over 4 microfarads plus 1 over 4 microfarads, and remember this is not C, this is only 1 over C. Okay, and now I get to flip both of these to get C equals 2 microfarads. Again, we're doing the 1 over thing in series because it's capacitors. For resistors, you just add in series. Okay, here, so we can sort of mess with this circuit a little bit. We can sort of redraw it like this. Right, we're allowed to introduce wires and junctions however we want, as long as we don't cross anything. So we see we have 2 things in parallel, followed by 2 things in parallel. So the first pair in parallel, you do 1 over 4 plus 1 over 4. Oops, sorry, these are capacitances, so you just add them. So the first capacitor is of size 8 microfarads, and the second capacitor is of size 16 microfarads. Okay, now you have to do 1 over C is 1 over 8 plus 1 over 16. Again, the mu prefix 10 to the minus 6, you can sort of factor it out from every term and leave it sitting outside. Or you can plug in everything with e minus 6 on it in your calculator. It'll still work. Okay, I'm going to do 1 over 8 plus 1 over 16. That's 3 over 16. And again, this is not C yet. This is 1 over C. So C is 16/3 when you invert both sides. And this is in microfarads. Again, we're carrying the micro around. Okay, I have this listed as an extra credit because we didn't cover it too much, so I think Paul and I agreed we're going to put these on as extra credits. Find the direction of the induced current in the loop. Now, as you can see on the equation sheet, like the main equation sheet, not the exam edition, the whole point of these problems is you determine which direction the magnetic field is changing in. So in this case, it's out of the page and getting bigger, which means that it's getting more out of the page. And the circuit doesn't like that. It's gonna generate a magical current and voltage that generates an into the page magnetic field to oppose the fact that the B is getting more and more out of the page. It doesn't like it. So we're gonna basically recast this problem as guess the current direction, guess and check the current direction that produces an into the page magnetic field. And again, it's not just because B is out of the page. It's because B is out of the page and getting more out of the page. It doesn't like the change, the fact that it's getting more out of the page. That's why it's that's why we're trying to cause a current that causes an into the page B field. Okay, and if we guess, I'm going to guess this way. So if I guess that I is this way and R from the creating element to some observation point is like this. Okay, if I do B is like I dl cross R. Let's see if I do that. I cross R, I get out of the page, so I actually guessed wrong. So the correct answer would be that I is in the opposite direction. Again, I was trying to guess an I direction that produces an into the page magnetic field, and I accidentally guessed one that creates an out of the page magnetic field. So I will actually be, I'll draw it in blue here, it's going to be clockwise. Okay, this is a Kirchhoff's laws question. So we're going to pick a direction that we're going to call the current and see what happens. I'm going to be intentionally dumb and get the direction wrong. And I'm going to assume that the current flows this way. I'm going to label the high voltage ends of every object using these current conventions. Again, batteries, you always put the high voltage end on the high voltage. Resistors, you put the high voltage on the upstream end of whatever current direction you define. And then the minus signs are on the other side. Okay, and now I'm going to randomly track the lifetime of a charge around the loop. I'm going to start at this blue dot randomly. Okay, so I gain 9 volts as I go up through this first battery, because I'm going from negative to positive. I lose 3I in the resistor because I'm going from positive to negative. I lose 18 as I go through the battery backwards, right? I'm going from the high voltage to the low voltage. I lose 3 through this resistor because I go from high voltage to low voltage. And then I lose 3 volts as I go from high voltage to low voltage in the battery. And I reach back to my starting point, so all the sums of all the voltage changes have better add up to 0. So I'm back where I started. Okay, so I have plus 9 minus 18 minus 3, that's minus 12, minus 6I equals 0, negative 6I equals 12, I equals negative 2. Now, I assumed I was in this direction through the top resistor, but it's a negative sign, so the actual current goes to the left, right? Because I guessed to the right, I got negative 2 in that direction, which means the actual current is 2 to the left. So I is 2 amps, and in the top resistor, it flows from right to left. Okay, this is another guess the magnetic field. So let's use a positive particle. You can use a negative particle, and the analysis is exactly the same because the negative particle will have a flipped response to both the E field and B field. So we're going to use positive particles, but it doesn't matter if you test a negative particle. So a positive particle would get pushed down by the electric field, right, away from the positives towards the negatives. So the problem is get a B field that makes a positive particle get pushed up. Okay, we're trying to guess the magnetic field that does that. I'm going to randomly guess out of the page, let's say. Okay, so I'm going to guess out of the page, and we're going to see what direction the force is in. Okay, so V is to the right. There's V. B is out of the page, so I do V cross B, and my thumb points down, so I got it wrong. So B out of the page doesn't make sense, as actually B goes into page. Okay, you might erroneously guess at first that maybe B points up. Well, if you do that and you do V cross B, you get that the force would be out of the page, so it doesn't cancel out that downwards electric force. You need to perfectly cancel. So you'll have to guess and check as usual with these. Another induction problem. So this time we sort of guess and check what B field was there, to make the induced current go in a certain direction. It's more complicated than the last magnetic induction problem we did. So again, I'm going to take the side of, I'm going to randomly guess and see if I get it right, and if not, I just flip my answer. So I'm going to guess that the magnetic field is into the page, and we're going to see what happens. And we're doing this in real time. I do not know what the answer is. I'm figuring it out right now. Okay, so if the magnetic field is into the page, and I'm moving the bar this way, the flux is getting less and less into the page because there's less area. Therefore, the current is going to try to generate an B field more into the page because it doesn't like that it's losing flux into the page. Okay, and if I check if this current generates a B field into the page here, here's IDL, here's R. If I cross IDL cross R, that actually does generate a magnetic field into the page. So into the page is actually the correct answer. Okay, and let's reverse work through this problem because I know this is going to be very confusing, also because I didn't teach it to my section in my specific way, and we went kind of fast through it. Just a recap of what's going on here. Circuits hate when the magnetic flux through them is changing. And in this case, I'm making the area smaller and the field is into the page. So the flux is into the page, but getting less and less into the page. So the circuit does not like that. And it's going to create a magical current that produces a B field that is into the page to sort of resist the change that's trying to happen. And a current in this direction does indeed create that more into page magnetic field. So the correct direction of the B field is into the page. Actually, now I'm realizing that I sort of was a little bit cavalier on guessing the direction of the B field. I'm actually going to go back now and intentionally guess the wrong direction and show you what's going on. Okay, so, So I was clockwise. Oops. Okay, I'm going to guess that the B field actually was pointing out of the page before. In this case, and we're going to see that the induced current would actually be in the wrong direction in this case. Okay, this is the actual induced current. The actual induced current is this direction. And we're going to see that if we had the B field set up like this, the induced current would have actually been in the opposite direction. So our guess that B was out of the page would be wrong. Okay, so in this case, the flux is out of the page and getting weaker. So the current is going to be generated in a direction that makes an out of the field, an out of the page flux, right? Because it hates the fact that the out of the page flux is getting weaker. So it's going to try and generate its own out of the page flux. And if we guess what current direction generates that, I'm going to guess that the current would be this way. We see that IDL cross R, the generated magnetic field, would be out of the page in this case. Okay, so the circuit in response to a magnetic field that was out of the page with the bar sliding, that circuit would generate an I in this direction, which is the opposite of what actually happened in the problem. So we know that our guess that B was out of the page is actually wrong. And the actual current is in the actual B field is into the page. Sorry for the clunky explanation on that one. Okay, question about solenoid magnetic fields. So equation for magnetic field near a solenoid is on the equation sheet somewhere. It's B equals mu naught little n, which is capital N over length, times I. Okay, we're talking about taking a solenoid and compressing it. So a very good tactic that we're going to use a lot in the class, and you probably have already used a lot, is when you're talking about taking something and either compressing it or expanding it, or just changing one or two variables, it's a good idea to divide the before equation by the after equation. So here's my original equation, and I'm going to write the new equation with the new variables here. Okay. We assume that the current going through the solenoid doesn't change, nor do the number of coils, only the length is changing. I'm going to divide these two equations by each other. Mu naught is unchanged, so it cancels. N cancels, I cancels. Okay, I get to dividing by a fraction is the same as multiplying by the reciprocal of this dashed fraction. Okay, so the new magnetic field B prime, I'm going to move, or here, I'll cross multiply if you want and then move things over. BL over L prime equals B prime. So I take the original B, which is 36 millitesla, and I multiply it by L, the original length, which is 3 centimeters, and I divide it by the new length, which is, L is the original length, which is 6 centimeters, and L prime is the new length, which is 3 centimeters. Okay, these two things they cancel out to 2, so all you get is 72 E minus 3 Tesla. Another alternative way, if you wanted to, is you start with this equation. You're given B and L. So you multiply L over to the other side, and you can compute what mu naught times N times I is. You don't know what each individual number is, but you know what mu naught times N times I is. And then you just plug it in here and divide by the new length to get the new B field. But this method of dividing equations to get like the ratio is very important. Okay, I'm now realizing I missed the formula for B field due to a wire on my formula sheet. So I'm actually going to have to rederive it right here. All right, there's my Amperian loop. B times the length of the loop, which is 2 pi r, is mu naught I. So B is mu naught I over 2 pi r. Okay. Okay, a couple ways you can do this problem. So you're doubling the distance, so you're making r twice as big, so B gets halved, right? You're dividing by a number that's twice as big. So that can instantly give you an answer of 5 microtesla. Another way you could do it to flex the muscles that we developed in the last problem is you take this equation and divide it by itself in the before case and the after case. Okay, the current stays the same, so I and I prime are the same number. I divide these two things. Everything but the r's cancel. I'm going to have to do some ugly movement of the r's here. Okay, move B prime over. Okay, r over r prime, original r is 20, r prime is 40, so this is a 1/2. So the new B field is indeed the old B field divided by 2. Again, ask questions on this methodology to me if you have concerns about it, but this is extremely important to understand that you can do this. It's also extremely powerful for conceptual questions, which are usually super deadly. And actually, we pretty much have the same question here. we have the magnetic field at point A. I shouldn't write B of A. We're going to think it's multiplication. B at point A is of size B0, and we're looking for the strength at site B, which has unknown strength. Maybe it'll be B0 over 3, B0 over 2. Now, we already know that B is mu naught I over 2 pi r. So if we make r twice as big like we have here, at point B, we know that the magnetic field is going to be whatever it was at A divided by 2. So that's the answer. But let's show that in variable terms. Okay, again, we're going to take the two equations, B at A and B at B. Okay, these two equations are each individually true. It gives you the magnetic field at point A in terms of the distance from the wire to point A. That's this little RA. And this equation down here is true for all the point B stuff. If I divide these two equations by each other, I get that BA over BB equals 1 over RA over 1 over RB. So I'm going to do the fraction flipping in my head. I'm going to move this over to that side and this over to this side by dividing through. Okay, RA over RB is 1/2, and B at point A is whatever constant we called it, B naught. So that matches the answer. Okay, so we're going to determine the direction of the B field at the center and then just compare it to a magnetic, like a bar magnet, a permanent magnet. So on top, it goes into the page, the current. So if I do I cross R, into the page cross down gives me to the left. So the B field points to the left. And if you do it on the bottom one as well, into the page is I, cross R to the observation point is up, into the page cross up. Oh, sorry, what am I talking about? This is out of the page. This is into the page, cross R gives you left, like I said before, sorry, this is out of the page. I forgot my notations. Out of the page, cross R, and R is up at this point. Remember, R is from whatever point you're currently considering to the observation point. So up cross, or sorry, out of the page, cross like vertically upwards, your thumb points to the left, so B is to the left. That means if you compare it with a like a permanent magnet, the B field looks like this. So the North Pole is towards the left of this ring. Magnetic field created by a point charge, you're going to have to use the Biot-Savart law, which, if you remember, is mu naught over 4 pi. So this is the B created by the point charge, is mu naught over 4 pi QV sine theta over R squared. Q is, it's a proton, so electron charge. V is 4,000. 30, and R is 3 centimeters, so 0.03 squared, and mu naught is 4 pi times 10 to the minus 7th, as usual. Punch all these in. Being very careful to group the 4 pi in parentheses. Gives me 3.56 e minus 20 Teslas. Okay, direction. The vector form of this is like the vector information is in this V cross R or QV cross R thing. So V is left, R points from the source to there, and you right hand rule these, left cross, and then you curl your finger slightly down. Your thumb points out of the page. If it were a minus charge creating it, then obviously Q would cause V cross R to, sorry, QV cross R would be in the opposite direction, but it's a proton. Okay, we need the current in these little wires in the cross section of a solenoid. We need to put them in the right direction to generate this B field. So I'm going to guess that into the page on top, which would correspond to the current going around in a loop, like it goes in on the top and then flows back out towards us on the bottom. Okay, into the page, B cross R, remember this is the Biot-Savart law. The B created by a current is like I dl cross R. So I goes in, R is pointing towards the observation point, and my thumb points to the left, so I got it right. So B goes into the page on top, edge of the solenoid, and out of page on bottom edge of solenoid. Okay, this is sort of a memory trick, or like just a memory exercise, because this is what we have been doing for a lot of the course, but for solenoids you actually can't do this. You have to use option B, because the magnetic field in a solenoid points like this, and it's 0 outside. So that's why you use this loop. You want this segment where B is the same size and parallel to the line everywhere. Outside a solenoid, the B field is 0, so this doesn't work. The B field points like down the barrel of the solenoid. It doesn't circle around. So this doesn't work either, because the line and the B field are in perpendicular directions. You need them to be along each other. And this doesn't work because you don't enclose any current. So all you learn is that the B field along each edge is the same size. So B is the correct choice. And again, the way you did the derivation in class is you're enclosing a bunch of like wires punching through here, like into the page or whatever. Oops. And that was how you did like I enclosed is like the number of turns times the length of the box or whatever. So that's how you did it. This is just a memory one because people forget it all the time. Okay, trying to find which direction positive charges get pushed. So velocity is down of the bar and any charges riding along on it. Force is QV cross B. Okay, down cross into the page gives me to the right. So the force is to the right. So positive charges get pushed to the right and negative charges get pushed oppositely to the left. So this right end here has higher voltage / more positive charges. Okay, we're going to combine the circuit. With resistors, you just add when things are in series. So I have a 4 and an 8. Okay, now I have to do the 1 over thing since they're in parallel. Okay, so 1 over 1/4 plus 1/8 gives me 8/3. Okay, so VIR next to everything. Okay, voltage at this one right down here is 16, right? That's the point of bringing it all the way to the battery. We learn what the voltage is. That tells us that the current is V divided by R. Which gives us a current of 6 amps. Okay, we're now going to work backwards. So we copy over, it was two things in parallel. So the voltage drop is 16 across each. This tells us the current is 4 amps and 2 amps. Now, I'm not going to do the whole thing, so I'm interested in these two. So I'm going to break this guy up, and I copy over the current going through it. Oops. Because I combine two things in series to get there. Two things in series share the same current as their resistor. Okay, and that actually answers the question, 2 amps. If I wanted to, I could finish the circuit, but I'm not going to. Okay, basic capacitance question. It involves the shape of the plate, so I'm going to want to replace C with the actual formula for capacitance based on geometry. And I know everything in here except one number. Okay, I don't know Q. A, all right, diameter is 4 centimeters, which means the radius is 0.02. So this is the area of one electrode. They're 2 centimeters apart, and the voltage is none. Okay, so this is how much torque on each plate. All right, direction of magnetic field. Again, the direction of magnetic field is like IDL cross R. So this guy on the left, he has I up and R towards the observation point. Again, I and IDL are pretty interchangeable. All right, if I cross product up with that, I get into the page. And I just want to double check that this guy gives the same one. He could cancel out, but let's see. He has I going down and R going from him towards G. So down, oh, I need to stand up to do this. Down, cross, left gives me also into the page. So both of them are creating into the page magnetic field, so they help each other, and the answer will be into the page. If I2 were going the opposite direction, then they would cancel out and give 0 if they were perfectly the same distance and stuff. Okay, I probably should add the resistor thing here. Let's write that down. Slide 24. Label resistor. I need a label. Okay, so the circuit's not closed. If it were closed, they'd be connected by a wire with nothing in between. So there would be 0 volts of potential difference. Sorry, voltage difference. But the circuit's open. This point right here has 9 volts of voltage, and this point right here at the bottom of the battery has 0 volts of voltage. So this point here is at 9 volts, and this point here is at 0 volts. So delta E is actually 9 volts. And you can view that the resistor doesn't affect it as there's no current flowing through, so there is no voltage drop, right? V equals IR. When there's no current flowing through the resistor, it doesn't cause anything to go through it. Power dissipation. Okay, I'm going to do the quick way to solve a circuit, which is to sort of, if it's just 2 or 3 things purely in parallel, you can just copy the 8 volts over because each path has to each individually lose 8 volts. Okay, this gives me an I of 2 amps here and 8 amps here. Now power, you can use a bunch of formulas. Like I didn't even have to find I could have done like V squared over R or whatever the formula is. But there's a bunch of ways you can do it. I'm going to use, I'm going to use it. I'm going to do that. Let's see, scrolling over to my power equations here. All right, so power is V squared over R for resistors. Again, you can use IR. I computed I once I had V and R, but you don't even need to do that. So V squared over R. For the left resistor, it's 8 squared over 4, which is 64 over 4, which is 16. And for the right resistor, V squared, which is 8 squared over R, which is 1. So I get just 64 watts. So the right resistor dissipates a lot more power. A pretty tough RC circuit question here. So we're going to want to calculate the time constant, and we'll be able to find the current and how it depends on the initial current. So this is just on the equation sheet. The current at any given time is the initial current times e to the minus t over tau, where tau equals RC. All right, and I0 is the initial voltage divided by the initial resistance, right? Because you assume that the battery has completely charged the capacitor. So initially you have this setup of, oops, sorry, I should actually reword this slide. The actual picture is more like this. There's a battery, a capacitor, and a resistor. Initially, the switch is set to just charge the capacitor up to 9 volts. And then you flip the switch, so you have basically a 9-volt battery here, and the actual battery is disconnected because this isn't a closed circuit, it isn't a closed loop. So you initially have like a 9-volt battery and a whatever R resistor. Okay, I'm just going to plug in numbers now. Voltage is 9, R is 2000, e to the minus 0.01 is like the actual time you're asking about, divided by R times C. R is 2000 and C is 1e minus 6. Okay, now it's just a matter of plugging this into the calculator. Okay, and I get an answer of 3e minus 5 amps. Okay, this one is just computing the time constant and determining which one, depending on which has bigger or smaller time constant, which one discharges faster. So we're just remember tau equals RC. So on the left, we have 24, so 6 times 4 with the micro on there gives us 24 microseconds. And this one gives us only 9 microseconds. So this guy decays a lot faster, right? After every tau, you drop like 60%. So this guy only takes 9 microseconds. This guy takes him up to 24 microseconds to lose the same amount of charge. So this guy discharges a lot faster. This is a tough one. This is my custom problem. Don't know what I'm going to do about this one. How long does it take the voltage to drop to 1 over e squared of its initial value? So we have a formula for the voltage as time goes on, and we're asking about time. Okay, I'm searching for the time at which v divided by v0 equals 1 over e squared. If you want to, you can move v0 over instantly in this equation. And then this is 1 over e squared, which equivalently is e to the minus 2. Now, if you want, you can take the natural logs of both sides. I'm just going to say 2 must equal t over tau. This is what you get if you take the logs and then cancel the negatives. Okay, so t equals 2 tau. Again, that sort of makes sense. If you plug in t equals 2 tau here, you get e to the minus 2. And that's how much you will have lost of your initial voltage, or your new voltage will have been your original voltage times that. Okay, and the time constant is RC, which is 10,000 ohms times 4e minus 6 farads. Which gives us 0.08 seconds. Just remark another way you can do this problem. You could say V equals 1 over e squared V naught, and then cancel V naught from both sides to get exactly back to here. Okay, relation between resistivity and resistance. Oops, do I not have this on the formula sheet? Don't know if I do. Okay. I need to pull up my slideshow here. Okay, resistance and resistivity are related like this. Resistance equals resistivity times L over A. Okay, we know every number in here except rho. Okay, so I'm just going to plug in numbers on the left here. R is the resistance. However, we actually are told the voltage and current through the wire. So instead of knowing the resistance, we're going to have to compute the resistance here. Or equivalently, I could plug in V over I where I see R, which is what I'm going to do. Okay, now I truly know every number in here. V is 8 volts. I'm not going to write V. Area of the wire, the area of the cross section, is pi times radius squared. Divide by current times the length of the wire. And I don't even know what this is in standard units. I don't even know what the standard units are in here. What will it be? It'll be like ohm meters squared per meter, so ohm meters. I know I say this on the homework, but I forget what it is. So I need resist. Okay, for my section only, terminal voltage. So all it's saying is the battery has another resistor attached to it. A 3-volt battery, a 1 ohm built-in resistor, and a 6 ohm resistor here. So the current through the whole circuit is 3/7. So the voltage drop across this 1 ohm resistor is the current of 3/7 times the resistance, which is just 1. So the voltage drop here is 3/7. So the terminal voltage, which is the voltage drop between here and here, is 3 volts minus 3/7, which gives us 18/7 volts. Okay, if you wanted, you could use the equation. It's like what? Big R over little r plus big R, where big R is like, I think, all the other resistors, and little r is the internal resistor. But again, I encourage you to not do that and just do it the circuit way. Okay, and last question, compute the voltage drop across 2 ohm resistor. So I'm going to combine into a 10 ohm resistor. Okay, the voltage drop is 10, so the current is 1 amp everywhere. Tells us a voltage drop of 8 volts in that one and 2 volts here, so 2 volts is the answer. Don't know why this one is at the end, considering you've done much harder problems already. Okay, again, this practice test definitely harder than the last one. Don't be spooked if you didn't do too well on it, or if you have a lot of questions on it. Remember, the real thing will be hopefully a little bit easier, and you will have seen all the questions before, so you should make it out quite all right. And of course, bring any questions to office hours or the help room. I know the long weekend's going to make it tough, so get a good group chat, and I'll see what I can do extra.